Okay, everybody, are you ready for the best lesson ever? It is here. All right, the evaluation theorem, or the fundamental theorem of calculus, is going to take the process that you've been doing with all of your problems of finding the integral, which is the area under a function, or between the function and the x-axis, from one x value to another x value. And it is going to take all the work where you took the limit as n approaches infinity of the summation as I goes from 1 to n of the heights times the bases, and you summed up an infinite number of areas of rectangles. Gives you a little shortcut to do instead. Okay, so pause here if you need to, write down whatever you want, but this is called the definite integral of f of x from a to b. Alright, so you already learned how to find an indefinite integral. It's called an indefinite integral. And that is when you take the antiderivative, and if you remember we had a lot of formulas we used in section 4.9. Some of you didn't need the formulas, but it's basically when you're working backwards, right? F of x, think of that as the derivative, and then capital F of x would be your antiderivative, and we used a plus c. What we actually want to start out with in this section is thinking of a specific function. If we want to think about the velocity curve and the area under a velocity curve, let me make a quick little, scenario here, a little what if. So what if a velocity function looked like that, and your velocity was measured in feet per second, and your time was measured in seconds. Okay, now think about what would the area under this curve be if we were looking at some a value and some b value. Well, you know that when you find an area under a curve, you're really just essentially adding up bases times heights of an infinite number of rectangles. So each base would be seconds, right? Because we're going to think of the units. And each height would be, look at your y-axis, feet per second. So if I was looking at from 1 second to 5 seconds, and I got the area under that curve, you can see how that's actually going to give me how many feet I would have traveled in the 5 seconds. Pretty cool, right? The other thing that you want to look at that's pretty neat is what is the antiderivative of velocity, because that's what we're doing, right? If this is the derivative, this is the antiderivative. If this is the derivative, the antiderivative is, I'm trying to give you time to say it, hopefully you just said it, is your position, is your position function. So it's s of t. Now, going back a step, which I can't in here, but you'll see that all I have to do is evaluate this from a to b, and that's a new piece of the notation, which just means plug in the top value minus plug in the bottom value. And that's how many feet you've traveled. Okay, units are super, super important. That was a velocity problem, but it goes with anything. And you'll see a strange example on the next page, or actually in a few pages. But whatever this is, in that case it was feet per second, you take the antiderivative, it's going to be called the total change theorem sometimes, and it's because if you think about the units here, you have a rate for f prime of x. Capital F prime of x is always a rate. dx is always just a unit, and when you multiply these units together, something's always going to cancel out, which gives you the total change, not as a rate. So again, pause this if you need to write that down, but let's get some concrete examples. With velocity, think about a velocity function. In the velocity function that I drew before, it was actually kind of boring, but I can have a velocity function that does this, right? And maybe think about it, representing the movement of a particle, right? So where the velocity is positive, your particle is moving to the right. Where the velocity is negative, your particle is moving to the left. But nonetheless, if you actually picture the motion of that particle, it's still moving, right? whether you're moving to the right, and then you turn around at some point and you move to the left, and then you turn around at some point and you move to the right. You've still done a lot of movement. All right, so let's think about what's the difference between this and this. Well, graphically, the absolute value would force this part to come up, right? Because anything that's negative cannot be negative, it would have to be positive. So essentially what you want to think of is, what's going to be the bigger value? There are two words, and hopefully you're thinking of them and remembering them from physics. But one of these is going to give you distance, and one of them is going to give you displacement. Okay? So if I just think about the position function, all this is what? S of B, we did this on the last page, minus S of A. That's just where you ended up minus where you started. Well, looking at this example over here, where I ended up was maybe here, where I started was here. All this is going to find is this distance. Now, I say the word distance, I use the term loosely. The distance that I really traveled was I started here, I went this way, then I went backwards, and then I went forwards. So I really covered all of this, and all of this for distances. The absolute value, if you forced the velocity to be positive, that would actually have accumulated all of that distance. So this is going to take some extra work to find. It's not going to be as simple as this one. But in general, you just want to know that this top one is going to give you your displacement. And that's super messy writing. And this one is going to give you your distance, your total distance traveled. Okay, definitely pause here, write these down, and if you want to, you can maybe just, try to put something over it, or don't look on the right-hand side. See if you can get these without looking at them. See if you can get the right-hand side. Just look at the left, write this down, and then before you come up with the antiderivative, see if you could remember, because it's just thinking backwards. All right, now here's where I said we can get into some kind of strange things for our rates. This first example says a honeybee population starts with 100 bees. It then increases, the population does, at a rate of n prime of t bees per week. What does 100 plus the integral from 0 to 15 of n prime of t dt represent? The easiest way to do this is always look at these units, okay? Those units are given to you right here. Bees per week, and you want to multiply them by these units, and t is just given in weeks. So all that integral represents is and I'll say it, you can write it, it's going to be the number of bees, that you accumulate during the first 15 weeks, from 0 to 15. And don't forget, you would have to add 100 to that because you already had 100 bees. So if this integral worked out to be, 75, then at the end of 15 weeks you have 175 bees. All right, I'm going to stop this video here, and then I'm going to do some of these examples, 10, 12, 14, 16. Actually, let me do one of them. Let me concentrate on this one. If you are feeling really ambitious, you can do this one using the limit definition. We can do the limit of the sum as n goes to infinity, as I goes from 1 to n, of f of x sub I times delta x. We can kind of do the delta x in your head, 4 minus 0 over n. And 4 over n I would be your x sub I, and this whole thing would be multiplied by 4 over n. You can try that and see what you get. What I'm going to do is use the shortcut now, and you can then compare them. The shortcut says I want to get the antiderivative of this function. Antiderivative of 1 with respect to y is just 1y. Then I have a 3 times a y squared over 2, one higher power over that power, minus y cubed over 3. If you don't know where I'm getting these, go back to your formulas. And I want to evaluate this from 0 to 4. So I have 4 plus 3 times 16 is 48. 48 halves is 24. Minus 4 cubed is 64 thirds. And then minus 0 plus 0 minus 0. So you could have just said minus 0. So I plugged in the 4 to the top first, the top number first, and then minus, I plugged in the bottom number. So what does this give me? 28. And I want to get a common denominator. So 28 times 3 is like 90 times 3 minus 6. 84 thirds minus 64 thirds equals 20 thirds. It's not super short, but it's definitely much shorter than doing this. Okay, so now I'll stop the video. I'll come back in the next one and do these 3, and then do at least some of these. I probably won't do this one. All you would have to do is square this quantity first, and then do the same thing I just did. We'll definitely look at some of these, and here's your homework. And there you go. Okay, so I will post this video first and then go back and put some examples up as soon as I can.